dilation visualized. I gotta put on my glasses for this, because this is a theory that I haven't been able to wrap my head around. And I've been hearing a lot of people say, just watch Interstellar and you'll get everything. I haven't done that yet. I'm not really a big movie guy, but I do want to get into it.
I love Project Hail Mary, but the movie glosses over what I love about Andy Weir's novels, and that's the science. I guess the general public is not into math and science, but I am, and I think fans of this channel are too, so let's do the math and nerd out even harder than the novel does on relativity, mass ratios, and the astrophage infection rate.
The what? You lost me. You lost me. I'm not that smart.
The movie mentions briefly that it takes him 4 years to get to Tau Ceti, but Tau Ceti is 12 light years away. So if you can't travel faster than the speed of light, how can you get there in 4? Well, that's where time dilation comes in. We can't travel faster than the speed of light, but something weird happens the closer you get to it. Time slows down. And if you keep accelerating, time keeps slowing down.
Hold on, because this you already lost me.
Constant acceleration is like the eighth wonder of the world. If you can keep it up, it's like
so all you gotta remember is that time slows down as you go faster. Oh, which means that I'll age slower if I'm faster. Does that mean Usain Bolt is... Oh, that makes sense. Bro, Usain Bolt might be the first person to reach 200. Oh my gosh. Oh, I'm onto something.
Interest. Extremely far away things become closer and closer because of this time dilation, which begs the question to me, how long would it take to get to Betelgeuse or the edge of our galaxy or the nearest neighbor galaxies? The answer is that we can travel anywhere in the universe within a human lifetime. Let's see it in action.
What?
Tau Ceti is 11.9 light years actually below us in relation to the galactic plane. But first, before we get to Tau Ceti, let's start with our closest neighbor. Let's start with Alpha Centauri and see what a hypothetical trip from Earth to Alpha Centauri would be like on the Hail Mary.
Oh, shit.
This orange
That's like
tube is not a wormhole. It's a representation of...
He just cooked me. He just freaking cooked me. He just cooked me! Bro, how did he predict me like that, bruh?
This orange tube is not a wormhole. It's a representation of how fast time is going for our ship relative to Earth. We start the trip accelerating at 1.5 Gs. And we get up to relativistic speeds extremely quickly. After only 5 months of accelerating, we're already going more than half of the speed of light. And while 5 months have passed for us on the ship, time has already slowed down, and 6 months have passed on Earth.
What?
By the midpoint, we're traveling 97% of the speed of light. And 1.5 years have passed on the ship, but more than 2.5 have passed on Earth. If we want to come to a stop at Alpha Centauri, it's here where we have to flip around and burn to slow down. And our time dilation will start going back to normal as we slow down to normal speeds.
Wow, I didn't even think about that, bro. So like, if you can move that fast, you can end up missing your stop entirely because you can't just stop on a dime like that. You have to plan halfway or else you're gonna miss the whole entire stop. But since time is relative to the velocity, as you go faster, the time gets slower. So since they went really fast here, the time dang near got cut in half.
But if we don't slow down, if we keep accelerating, time keeps getting slower.
So you could technically reach there faster, but you just can't stop now.
As we keep accelerating, our velocity tapers off because we can never get past the speed of light. It's asymptotic. We just keep adding 9s to our 99 point.
Hold on. Wait, hold on. Give me a second. Oh yeah, asymptote. I learned about that in school. Y'all, I don't know about y'all, bro, but once I graduated, it was as if I paid for a subscription. I don't remember nothing about asymptotes. I don't remember nothing I learned in chemistry. That's all the knowledge just leaving my freaking brain, bro.
Asymptotic. We just keep adding 9s to our 99.9 whatever of the speed of light. But the time dilation doesn't taper off. It's not bounded. The more we keep accelerating, the more time slows down.
It's just, like he said, it's asymptotic, so you're just infinitely getting faster in a sense, but you're not going past the speed of light. Is that right? But since you're infinitely getting faster, that means also that the time is infinitely going to be getting slower relative to the velocity that you're going. I think that's what he's saying. Y'all, I'm dumb, so just again, and this is stuff that I want to learn about, so just let me know if I'm wrong You know, anybody who's, you know, well versed in this type of stuff.
Perspective, it's exponential. Every additional year of acceleration, the time dilation roughly doubles.
Oh, wow.
If we compare the trip to Alpha Centauri to the trip to Tau Ceti, we can see this in action. The trip to Tau Ceti only takes about 1 year longer than the trip to Alpha Centauri, even though it's 3 times farther away.
Literally.
Rocky's trip from 40 Eridani took about the same too, because they're about the same distance from Tau Ceti than we are. They're about 10 light years. So the time dilation is pretty much the same if they took the same flip and burn profile, which they didn't. But to really see the power of this, we need to go much further. Betelgeuse is about 500 light years away.
What?
With the same level of acceleration, the trip would only take 8.5 years.
Wow.
At the midpoint, we will reach 99.999%
That's,
of the speed
look
of
at
light.
it. So it's just, bro, see, like this is where it just gets to a point where it's too much. 498 years, everyone you love will be dead. What will you have in 500 years? No one. You're not a Viltrumite.
I've scaled up the travel lines, but as often the case with cosmological distances, things are getting hard to see. To really understand the exponential nature of this, we have to change the way we're looking at this. We've got to move the stars around here. Let's compress everything based on how long it takes to travel to them. In order to illustrate that, let's add in some more stars, like the Pleiades cluster, which is a famous star cluster, slightly closer than Betelgeuse, and the Orion Nebula, which is 1,000 light years further than Betelgeuse.
This is nuts.
When we engage our time dilation, this is what happens.
What?
Remember, the farther away an object is, the more time dilation affects it.
You've lost
So the
me.
Pleiades and Betelgeuse are only slightly further than Tau Ceti and Eridani, and the Orion Nebula, which was 1,000 light years further, is now just slightly farther than Betelgeuse. Betelgeuse took 8.5 years to get to,
Right,
and the
right,
Orion
right.
Nebula only takes 9.5.
Because
you
it'll
can
get
now see
slower.
how it's getting squished up around the
Yeah,
edge, and
yeah, okay,
that's
yeah.
the same thing that's going to happen for the rest of the stars in our galaxy. Our entire galaxy becomes a squished shell right on the edge of our doorstep.
I'm understanding now. The further it is, the more squished it'll be. So if you just keep going,
Other galaxies too get pushed.
By the time you're like 15 years in, I feel like dang near everything in our galaxy is gonna be very compressed and squished together in terms of how far you have to go to really get there.
Other galaxies too get pushed right to the edge. The Large Magellanic Cloud, which is 160,000 light years away, takes 16 years.
Dang.
Andromeda, our closest large galaxy, which is normally 2.5 million light years away, takes just under 20 years to get to. The Virgo cluster, a cluster of a couple thousand galaxies, which is 54 million light years away, would take just 23 years and 7 months.
Yeah, I do see like the spherical shape.
And
that it's
finally,
creating.
the edge of the observable universe, 46.5 billion light years away, would take just 32 years and 3 months.
Dude, that's
At which point we will be traveling 99.9999999999999999999.
Yeah, just keep going. Yeah, just keep
21
going.
nines. The speed of light. And 46.5 billion years would have passed on Earth because we're basically going the speed of light.
Billion? Oh my god.
This would require.
And then you could, bro. And then if you were to go to the edge of the observable universe and then travel back, what would that have been? 50 years? Bro, by the time you make it back to Earth, what if you come back and your species is just gone and you see dinosaurs again? Or what if by the time you get back to Earth and it's been 50 years for you, but relative to the time that you took to get to the edge of the observable universe all the way back, that's like, what did he say? 2.5 billion years? Bro, humans aren't going to exist. I'd be surprised if they did. We probably would have gotten wiped out either from nuclear warfare or, I don't know, a new predator or something, AI, who knows?
This would require a lot of energy. Actually, in this example, it would require a lot of matter because that's what we're doing. That's what astrophage is doing. It's converting matter into energy. Astrophage is like a little E equals MC squared bioengine. So how much matter do we need for this trip to the edge of the universe? About 500 sextillion tons, which is the mass of 87 Earths. And this starts asking the question, how much mass is too much? Because we're already idealizing a lot of things here. In modern rocket engineering, a mass ratio of 20 to 1 is considered realistic. That means the fuel weighs 20 times more than the ship. And in fact, that's exactly what the mass ratio of the Project Hail Mary was in the novel. The ship needed 2 million kilograms of astrophage to reach Tau Ceti in 4 years. And the ship weighed 100,000 kilograms, 20 to 1. Problem is, that was a mistake by Andy Weir. 2 million kilograms is what was needed if it was a flyby. To stop at the destination, you need to square that number. So what it really needed was 400 million kilograms. I reached out to Andy Weir and he responded and confirmed this, which would mean a mass ratio of 400 to 1, which is a little unreasonable. But we do have an option to save some fuel. We don't need to accelerate for the whole period. And that's what Andy Weir says he changed. He said he added a coast phase. Okay, so let's do the math. Using the same specs from the book, 1.5 Gs of acceleration, if we coast for 85% of the time, that is, we accelerate for about 1 light year, coast for 10, and then decelerate for 1, we'll get there in 6 years and 8 months. Confusing to me, in the movie, they didn't fix this. There's a point at which, at the end, the computer says it's going to take 4 years or 2 months and 11 days.
I want to watch this movie now.
Which is almost exactly a 50% coast phase. So that seems intentional to me. Like maybe that was Andy Weir's fix to do a 50% coast phase. But with the 50% coast phase, the mass ratio becomes 124 to 1, which would mean the ship would have had to have weighed 16 tons dry or used more astrophage. And in the movie, they say it still uses 2 million kilograms of astrophage. Dang. But honestly, there are so many assumptions we're making here that 124 to 1, maybe that's plausible in this universe, holding astrophage. You can play around yourself with these numbers on my website.
You have lost me. He's just talking gibberish at this point. I don't know what he's saying.
Later on my website. Either way, I'm still inspired that it's still physically possible to reach other galaxies within the known laws of physics. Because there could be other methods of generating insane amounts of energy in the far future, like a Kugelblitz drive or something else crazy. And we could still get there without wormholes or breaking physics. While I'm in the mode of being an armchair physicist, there is one other flaw in Project Hail Mary that I thought was interesting. In the story, Tau Ceti is the only star nearby Earth which is not dimming due to astrophage infection. Canonically in the novel, as they're tracing back where it came from, they say that the sun was infected by WISE 08550714, which was infected by Sirius, which was infected by Epsilon Eridani. They also say that WISE infected Wolf 359, the Land 21185, and Ross 128.
You know what I find crazy, and I'm not sorry for pausing actually. I genuinely enjoy people who take their time to learn this type of stuff just to make their movie at least a little bit more plausible. Even if people like this could come out and like refute claims because they forgot to look at this or they forgot to look at that, and it turns out that the movie wasn't 100% accurate, I still find it really nice where there's just regular people who want to have a take on this type of thing. So they take their time out of their day to do the research and find out what this galaxy is named, what this planet is named, what this sun is named. In my head, it's so hard for me to wrap around the fact that if there's billions, how do you not mess up getting, like, how did you not mess up getting one of their names wrong? Like, what if WISE 0855-0714? What if you're like a light year away on the telescope a little bit, so you messed up, and now everyone's calling that WISE when WISE is really right behind it to the corner because it looks the exact freaking same.
Deduce that the range at which astrophage can survive interstellar distances is 8 light years, and thus the range that it can infect other stars is 8 light years. Problem is, in real life, WISE...
Astrophage is a fictional alien microbe from Andy Weir's Project Hail Mary that acts as an interstellar mold or algae, feeding directly on the surface heat of stars. Oh, that's gas. So I guess the whole premise of the movie is that he has to leave that galaxy. He has to leave Earth because that entire belt, the orbit, is cooked because the sun is being eaten alive.
This is 11 light years from Sirius. Ours is 8 light years. Problem is, in real life, WISE is 11 light years from Sirius, so that's a no-go. The shortest distance from Tau Ceti to Sol in less than 8 light year hops would have been Tau Ceti to LaSalle 9352, LaSalle 8760, Ross 154, Barnard's star.
Oh, so that's
and
the
Sol-
path that
I feel like I'm playing Elite Dangerous.
algae took.
But that wasn't actually the problem that I thought was interesting. The problem is that if 8 light years is indeed the infection range, 90% of stars in our galaxy have another star within 8 light years. It's, in my opinion, probable that astrophage would have spread throughout the entire galaxy like a plague, infecting nearly every star. It sort of depends on the distribution of stars, and there are some filters that could have limited it, but I just thought it was interesting.
Yeah, because there's so much stars in the universe. You see what I'm saying? So it would have eventually spread to the entire universe. Maybe like what this guy is saying, with the exception of like, I don't even know. I don't. It's so much numbers to the point where you can't really calculate it off of just guessing. I don't know. We need Einstein back. Bro, who's the modern day Einstein? I really don't think smart people have clout anymore, bro. Because Einstein got clout. Who's the modern day Einstein? I haven't heard of nobody who came up with no crazy revolutionary thing since Einstein and Isaac Newton. You feel me? Hey, me personally, I mess with Neil deGrasse Tyson. He cool. I mean, he cool. I'll be watching his videos.
To visualize what an 8 light year range spread would have looked like in our nearby stars. This is using the ATHYG stellar catalog, by the way, which is not a full representation of all the stars in our neighborhood.
So these are actual stars in the network? Oh my gosh, that's crazy. Oh, that's it? Is that it? Okay, add at the end. Dang, that was a really good video, bro. That was a really good video. I got a lot of stuff out of that, bro. I really like that video, bro. Oh my gosh, bro.